we're now getting down to another series of attacks attacking session management. So the issue here is, there was a time when the web was not personalized, called Web 1.0, but we're long past that. Now everybody sees a different web page. If you all go to Google or Yahoo or something, you each see a different web page. It's targeting ads. It has some place where you can log in, and then you see your own authenticated content. And so this means there has to be some way to preserve that information. So the maintenance of a session is clearly a prime target like authentication. If you could overcome the session manipulation, then you can get into other people's accounts, like perhaps even the administrator's account. So that's the point. Users can masquerade as other users and go over to the administrator, and this might be as simple as just changing the value of a token, like the user ID. They used this technique to get in my Gmail account at DEF CON. I was on the wall sheet. I haven't found a picture of my name on the wall sheet, but it was there, because this was when they brought out Hamster and Ferret. And this is a time when a lot of people like me did not know that Google just uses a token transmitted over HTTP after you log in to authenticate you, and anybody can just steal that token and get in your account. They don't get your password, but they hijack your session. And Google, a couple years after this, did upgrade to 100% HTTPS all the time, so this attack became less practical. Anyway, so you need a state, right? Web 1.0 was stateless. You just put up static pages and everybody look at them and just see them like billboards. And that was kind of fun, but it's not much fun because you don't have any IMs or email or anything personalized. So people moved up to Web 2, where people can log in and then put comments on boards like Facebook and all that jazz. And this means we now have to remember that you have logged in and I know who you are until some time comes when you've logged out or the session times out or something. And I have to make this automatic so you don't have to keep putting your password on every page. So even if you have no login, there's often things where I still need to know who you are, like you're shopping. And you're going to put things in your basket, and then you're going to hit pay, and you're going to have an option probably of paying without creating an account, just putting in a credit card number. And so I still need to know who you are. So you're still the same person to put these 3 things in the basket and different than that person over there, even if you didn't log in. So it has the same issue as a session. So the most common way you do it is with a cookie. When you send to the server will then send you an ASP.NET session cookie, which is this long blob of base64 junk. And then every time your client makes another request to the same domain, it will send the cookie up. So the cookie is repeated back to the server, and that tells the server who you are in some way. And of course, the whole point of this chapter is that people often use foolish methods of using a cookie to figure out who you are. So there are vulnerabilities. There's 2 ways to do this wrong. One is to make the token in a way that is not random and can be predicted or guessed. And the other one is to not handle the session correctly, so someone can jump to another session or steal some kind of session identifier or predict a session identifier to get into somebody else's. So now a lot of software automatically generates these things, and the app doesn't use it. So there's the ASP.NET and other PHP cookies and stuff might be flying around that are just useless dependencies from the viewpoint of the developer because the management system created it, but they actually keep track of your session another way. So the way to find out what session actually matters, what token matters, is to find a request that returns a page with customized content, and then start deleting the cookies and replaying the page until you find out what you delete that makes it forget who you are. Then you can tell what part of it is actually important for this. This is the general philosophy of black boxing an app. Since you don't have access to the source code, you have to just feed it inputs and see the output. And this is the simplest kind of reverse engineering, where you don't attempt to understand it in any detail. You just find out what inputs lead to certain outputs and deduce how to get things done that way. So there are alternatives, by the way, to sessions. HTTP authentication just automates this process. In the header, it will send digest authentication or basic authentication or NTLM hashes in Windows domains, and that's how it works. It's automatically sending your authentication with every request to the server, so you don't have to keep logging in as you go to your Exchange server and your other Microsoft products. But this is not normally done over the web because people, it's intended to work because you've logged into a domain controller at one company and you're accessing the company resources for that company, not over the whole internet. This is sort of like what Obama wanted to do when he said the U.S. government would issue you a password and you would authenticate to the U.S. government server, and it would become your password to everything on the internet, so you don't have to remember so many passwords. And that has just been stalled in people yelling and screaming about what the hell, that's crazy, how are you going to do that? And it looks like it's going nowhere, which is probably just as well, because that does sound like a terrible idea, just fraught with problems. And that's why this doesn't happen either. We can't all agree on one domain to all log into and trust that to handle everything everywhere. Instead, one company wants its own domain controller and they don't want to trust information from another domain unless they're really a close business partner. And then you take, Microsoft makes these things called federated identity management servers that you put on your system so that you can send a token from the other company that is accepted at your company for some limited purpose. And but you don't just want to accept everything at face value that some other company determines. All right, so another way to do it is transmit all the data required to manage the state in the client for the ASP ViewState. The ASP ViewState does this. Here's some of the code from Microsoft documentation about ASP ViewState. You make a whole array of items, all these things, item 1, item 2, item 3, these are things you want to know about people, like what they bought in their shopping cart, and so what their username is and stuff. And you put it in this thing called a view state. And it automatically creates it, and the view state is just a big binary blob with no apparent structure that includes all that information. You can put in anything you want, hash tables, integers, numbers, Boolean values, and it all gets converted into this long blob of base 64. And it can even be signed. It's not encrypted, but you can sign it with a digital signature that includes the MAC address, so the server and some other things, so it's unpredictable for all practical purposes. And that means if somebody does convert it back from base 64 and alter it, they can't make the signature, so it'll refuse to accept it. So you have an integrity check. It's not a confidentiality check, but it's an integrity check, so nobody can alter the view state. Yeah?
Can they view the signature in the MAC address that was used?
You can never view a MAC address. That's one of the great things. MAC addresses never leave your LAN.
No, I mean, like, since it's signed with their MAC address?
It's signed with a thing that includes your MAC address and the time and the milliseconds, I think when you get your first connection or something. So they take several numbers and mix them together, and they use that to create a key, which they make a signature with.
And is the key,
it's not completely random. It's somewhat predictable. If you actually could, like, get a shell on the server, you could probably get enough information to get the MAC address. But you can't just send requests yourself and look at your token and figure out somebody else's token from that. That's the idea. And you can't figure out what the MAC address is from that. That's the idea. Although people certainly try. And one thing we might argue about is the MAC address is not enough entropy. It's 48 bits. And 48 bits is, if that was the only thing, it might not be enough. But it raises the bar. But if you really had to hack this, it might be possible. So if you want to see if people are using this, they'll have some blob of data more than 100 bytes long, which is all full of a whole bunch of data, not just a ID number, but all kinds of data is probably packed in there. And it'll be encrypted, so it looks like it has no structure. It might be signed, and the application will reject. If you try to reuse your token for some other request, it'll reject it because it's stored information in there. That'd be a clue that that long block of binary is actually a sessionless state mechanism. That's when they catch when they're doing this sort of thing. Anyway, token generation. Here's things you can do wrong. But there's first how important. Now, you need tokens everywhere. When you have password reset, they have to send you a URL with some long random token in it. When you want to prevent cross-site request forgery, you put hidden fields in tokens to make sure that people are actually coming in from your page and not sending a request to some other domain. You have one-time access to protected resources, and you have the opposite of persistent token, remember me, so you don't have to keep logging in again. And you have, if you want to see the status of your order, so what's in your shopping cart, then they have to send some token to identifiers. These are many of the use cases. It's just many functions require them to figure out who you are, and they all rely on this token. So if they're able to somehow defeat your tokens, all these things are shot, and you can totally mess with other people's accounts. So meaningful tokens is one of the major mistakes people make. They take something like this. So here's a token that looks like a long random string, but if you've been playing the CTFs or anything else, you notice that 73 out of 73, 65, 72, those are ASCII letters. And in fact, if you just look them up in an ASCII table, 75, 73, 65, 72, in hex is down here, that's USER. So if you just trace it out, this thing is user equals DAF, app equals admin, date equals 10.9.11, then just convert it into hex. So it's not encrypted at all, it's just encoded loosely, and therefore you can easily modify it. I can change the username, change the date, things like that, and I might be able to get in somebody else's account. So here's things people often put in these tokens: username, some kind of user ID, which determines who the users are, because you don't usually uniquely identify a user from a username, because two users might have the same name. There's usually a number underneath it. Email addresses, their role, like whether they're the admin or not, and other things in there. So Then they encode it somehow. They could just be hexadecimal ASCII codes, or they could try to obscure it a little bit by putting it in base 64 or XORing it with something, typically only a 1-byte key. And so the trick, so if you want to follow for these, go to the website and log in and mess around until you get a token that identifies you, and then just start modifying it. And see if the modified token gives you, see when the modification, if you modify the token, if you hit an unimportant part, it'll still load the page. If you hit an important part, it will say you're invalid request or you're logged out. And if you hit the right one, you'll be in somebody else's account. So you just try these things, modify them. And Burp has a thing called character frobber that will do this automatically. Other things, most see some versions of similar attacks in Burp going by. Another thing that's fun is log in at different times and see if time matters. Log into several users and see what that has. And if you can make accounts with simple predictable names like A and A and A and A and A, and see if there's a pattern in the token that's created. Look for correlations in the token. So one thing to know is if you use XOR, repeated characters will remain repeated. The A might turn into a Z, but the next A will turn into the same Z, so you'll see repeated characters in the input will turn into repeated characters in the output with single 1-byte XOR. Base 64 has always the same character set, uppercase, lowercase numbers, and a couple of symbols like slash and plus, and most of the time it ends in equals or equals equals as padding characters, so that's pretty easy to spot. So try to guess the tokens of other users. So you find a page that's session dependent, and then you use Burp Intruder, which will let you send a request over and over and over and log facts about the result, like how many total bytes there were, and just look for one that's different. So I got a few iClickers about that. Come grab one if you need one. They're over there. And here. Two-fisted. You know, that's an attack. You could have like 5 of them and hit A, B. Yeah, you have a correlation issue. I don't know. Might be a way to get a higher score that way. Anyway, so all right, there's. All right, yeah, if you had a pile, of them, you had some pattern, you might be able to. Yeah, I don't know. Anyway,
you could just.
Yeah.
The ones I don't know, at least got a 50-50 shot on them.
Yeah, so you could always choose the first one here and the second one there, and one of them have more. Anyway, so all right, so come on. Yeah, don't ask me foolish questions. Okay, there we are. All right, so the web app turns that into that. What kind of encoding is that? I see why. Okay, good. All right, I'll quit it for 45 down here. Looks like the answers are in. All right, that is base 64. And let's talk about it. Now, base 64 does not always have the padding characters. It's the only thing missing here. But what it does is base 64 uses 6 bits at a time. ASCII normally is interpreted as having 8 bits at a time, although it really only uses 7 of them. So this is 1, 2, 3, 1, 2, 3, 1, 2, 3. There are 3 groups of 3 characters there. And every 3 characters with 8 bits in a byte turns into 4 characters of base 64. So USE turns into GXNI, and R equals A turns into CJ1B, and AAA turns into QUFB. So there are no padding bits needed because it had an integral multiple of 3 here. But you can tell this has got uppercase, lowercase, numbers, and therefore it can't be hex. And if it was XOR, you'd see a pattern. So it is in fact base 64, but it's good to get some practice spotting it. All right. Anyway, how about this one? All right, guess I can quit. Let's see if the answers are in. That is none of them. That is, in fact, MD5. That's not simple hexadecimal encoding because it would be much shorter. It's got many more bytes here than that. That's none of these simple encodings. Okay? And the E, that's a bit extreme. Anyway, so, all right. Let's try this one. There we are. What do you think of that one? I think it might be an error in that one. Yeah, there is an error in that one. I'll fix it. There. Now it's right. Something went wrong with my script. All right. Looks like I can quit. All right. That is X. That's hex. You can see the AAAA at the end for the AAAA. 41 is the hex for A. All right. A popular answer. All right. And what do you think of this one? Which has the same mistake. My script stopped at 8 characters. I didn't count them correctly. All right. I'll quit at 30, I guess. All right, and that's XOR, because patterns are, well, stop that. Patterns are preserved, but altered. So 4A's turn into 405s. Yeah?
Can you go over XOR encoding and just explain me how it works? Because I know XOR encryption, but that's not
The same thing. So it's not encoding, it's just encryption. So you turn it into ASCII, you turn it into hex, and then you XOR it with a key. So this key is 44. So you flip the third bit in each nibble. That's all it is. So first you make hex, then you XOR it with a key.
XOR, it's hexadecimal representation.
Right, ultimately it's binary. You take the binary representation and you take a key and you XOR it with the key. And typically, in most cases, it's just a 1-byte key, which is the simplest. It could be a multiple byte key. But most of the time, this is a simple 1-byte key, which is why whatever it is that turns A into 5, it turns the next A into 5, and the next A into 5, and the next A into 5, because you're using the same 1-byte key over and over.
So the key should, for it to be stronger, it should be longer?
Yes, a longer key would be stronger, and in fact, something like WEP uses a pseudo-random sequence that never repeats for the key. And that's what you need to do. Yeah.
Can you show an example of that?
What's that?
Can you show an example of how you would do that?
Yeah, it's coming up later. I mean, I know how to do it in Python. Yeah, it's actually pretty easy. In fact, you don't even need to write it hardly. You can just do this. In fact, yeah, I think I got it right here. So if I just use interactive Python, let me get out of here. Okay, so if I want to do this one, let's take this. And, all right, if I do Python, okay, and I set input equals that stuff. Let's blow it up some more. All right. And then I can just do import base 64, the library that does it, and then I can calculate base 64 of dot B64 encode of input. There's that one. Now, if you want to do XOR, it's actually a little bit annoying. I think that's what I have here. It just turns out you have to take, you have to convert each byte to hex, and then and you have to do a lot of flipping back and forth between int and hex. This is the XOR operator. In fact, this is how I did it. I did it one nibble at a time. I turned it into, I took each character, one character, and interpreted it as a hex number, put a 0x in front of it, and then I made it a hex value here after XORing it with 4. That's what I actually used to do it. The only part that's annoying is you have to keep flipping back and forth between hex and int.
Could you use Borg?
And string.
Could you use Borg for that?
Use Borg?
Borg for each character?
You can, yes, if you start with characters. Here I was starting from hex. Yeah. So that's actually the script I used to do it. It's just kind of annoying. You have to add a 0x so it understands, and you have to strip it out later. Yeah. All right, good. And I'll have another example coming up later, more of these transformations, because there's a sort of very difficult one in the book, which I have not put in your homework yet, and I may not. I wonder how often this kind of nonsense really happens. So predictable tokens, right? So if you have a series of tokens, if you just go to the page and wander around and make a few accounts and log in and out and stuff, you get a sample of tokens. Then you can try looking at the tokens to see if there's a problem. Now, if you're doing it on a live server, you might have a problem getting a large amount of tokens because they might lock you out or something. And if you can do a local install, then you can really, get thousands or millions of tokens if you want. Now, if there are sequential tokens, Burp has the ability to attack these directly. And so here, it's just trying all these requests, and it's put 0, 1, 2, and 3 down here because they had identical responses, and the ones that were different, it put them on top so you can see them. And this one here actually had different names being logged in as. So it's just going through, like from 1 to 147, trying all the numbers, and these numbers actually led to a long response with a name in it. So you did get in other people's accounts. This is the simplest kind of attack. All right.
Is there a way in Burp to point it somehow to a URLs?
Yes.
And let it know which portion of the URL it want to see, and it will try to
Yes,
handle it?
that's exactly what you do. Yes, that's Burp Intruder. You can do it. You can highlight this part and say that's the URL. Now I know how to do it in Hydra, which I think is what you're going to have to use, because if it's like the other ones, I think they cripple these functions in the free version. But yeah, you can of course write a little Python script that does the same thing, and that's all it's doing, is repeating the URL and changing these characters according to the pattern you choose. So I haven't got a project where you do this stuff. I'm going to play with it and see what you can do in the free version. But writing it in some kind of language is probably the most practical answer. So here's ways to get predictable tokens. One is you have sequences that are just counting through numbers, but it's concealed somehow. You can also use the time to make a supposedly random number. And you can use random number generators. Now the problem is there's nothing really random in a computer. A lot of people have argued about this, and in fact I think the Pentium i7, or the Intel i7 I think, now has a hardware random number generator in the processor, because people got so upset about there are a whole series of serious flaws in security caused by non-random numbers. So a hardware random number generator is a very simple electronic component. If you run current through a resistor, the atoms in the resistor move randomly, so the actual amount of current varies up and down to random amounts. You run current through a resistor, and then you amplify the noise until you get clipping bits. And you have really random bits, although I think if you wanted to be pedantic, changing the temperature of the computer might have some effect, and putting it in a strong magnetic field might have some kind of effect. But for all practical purposes, those are really random numbers, as random as somebody flipping a coin or something. They're not dependent on anything. And but now, the Snowden stuff came out, and a bunch of people freaked out and said, maybe the NSA poisoned the Intel hardware number generator, so we aren't going to use it. And it's very hard to prove that the random number generator is really random. There's actually almost no way to really know that. And the NSA did poison the random number generator for ecliptic curve cryptography. That's how they got in. And Bruce Snyder said if you wanted to have a secret backdoor in encryption, this is probably the best way. So anyway, it just depends on how paranoid you are and whether you're trying to hide from the NSA. Like I say, I wouldn't bother trying to hide from the NSA. I mean, they are the smartest people on earth with all the money in the world. And if they want your stuff, they're getting it. But anyway, so here's an example. And like I say, he actually, I think if you pay his money and run his samples, you could actually try to hack into this example. And I could write it, but I'm wondering how often it's like this. Anyway, so here's the sequence of tokens. Apparently no pattern at all. But it's obviously base 64, because it's got uppercase, lowercase numbers, and I think even a plus in there. So if you reverse it with base 64, it turns into non-ASCII unprintable crap. Well, that might look bad, but it doesn't necessarily mean you're not getting anywhere. You just have to put it in hex. So if you take those ASCII characters and put them in hex, a lot of them are not ASCII because the printable characters only go up to 7F. Everything with 8 or more on the left is not printable, but they're still bytes. And again, they look random. But what you can do is calculate the difference between sequential numbers in hex. And when you do, the difference is always the same. 97C40, all this is what's called a linear congruent series. It is just adding a constant amount to numbers and then taking the lowest order 32 bits. And if you add a sort of non-even number like this, then you'll get an apparently random series of numbers, but in fact they're easy to predict. And once you've figured this out, you can take any one of them and predict all the ones going forward and all the ones going backward. So you can totally get everybody's session. And here's the script that decodes this. And like I say, if you want an example, I put it all in here. So here's base 64. You start with the raw junk, then you decode it this way, base 64 decode. And I had to add the equals to it because he didn't do it here. Technically, these things have to be padded because base 64 has to be groups of 4 bits, 4 characters, which will decode to 3 bytes. So that does it. Then you want to convert it to hex. So now I know it is 8 characters long. So I think here's where I accidentally lost a character or something. Anyway, I think there's only 7 characters long at that point. So now I just do ORD of the decoded bit I, and I turned it into hex. And since I turned it into hex, it was fine, but one of them was B, not 0B. So I had to add the leading 0 in. So the solution to that I learned long ago is you add 256 and then take the right 2 characters. When I worked at a company where we had these numbers, code numbers, claim numbers for claim forms, and I thought you'd start 1, 2, 3, but they never do. They started at 10,001, 10,002, 10,003 for exactly this reason, because you don't want the total number of digits to be varying. So you start at 10,001. Anyway, so this is how I get a 2-digit character, which is the hex, and then I just append them and I get the hex here. Then I gathered the hex digits together and made one long hex number, and then I had to calculate the differences. So now that I have a long number, I just take the n1 minus the n plus 1th one, and then if it's less than 0, I add a big number to make it positive again, and that's what that FF in the front is. So it's a little bit irritating, but I don't know why he chose to do this. He chose to represent negative numbers with an extra byte here. And I don't know why he'd choose one, but that's what he chose. This is 4 bytes, and he chose to use 5-byte precision when calculating this. But anyway, that's all right. This just lets you see that it's really always the same number being added over and over. Anyway, so that's the game. And there's the script to decode. And so now I could generate valid tokens with just this. I take one valid token, like I could get one out of my own burp, and then to predict the next 7 of them, I just add this number. And if it's too big, I take away that big number to rail it back, and you get a whole series here, which is the same numbers we started from in hex. So it looks random, but it's not random at all. These things are actually just the lower order bits of a linearly increasing series of numbers. So that's one thought. Now here's another example from, sounds like an online shopping site he was doing. You have 2 numbers, and I'll separate it by dash. The one on the left just increments 1 for every user. Every session gets 1 more higher, so that's not surprising at all. The one on the right is going up, like the left part. 11727 is always the same as 718, 062, 281. It's jumping up by larger numbers, and here's the difference. It's jumping up by numbers like from 1 to 300 that are apparently random. And so then he waited 10 minutes and got another set. Now, the number on the left has jumped by 6, so there have been 6 users in between. Number on the right has jumped up by 600,000. And 600,000 is the number of milliseconds in 10 minutes. So the number on the right appears to just be the time in milliseconds. And so that means if you want to break in, it's real simple. Just set up a cron job or something to pull the server at regular intervals, and then you can tell how many people have logged in between your 2 points by how much the one on the left moved, and you can just try all the time values from your first time value, next time value, and one of those will be right. And you really only have to try a few hundred values to break into each one of those sessions. So that's the point where time by itself is not very good, unless you have no clue when something happened. All right, so that's one way. Jetty apparently did this. Jetty used a linear congruential generator, and what this did, here's the math that it did. It starts from a number, and it multiplies it by this number and adds a constant, and then takes the lower 48 bits. And so it's really nothing more than the one you saw before. It's a linear series of transforms, and once you know it, if you have the code and know these numbers, then if you have any one example, you can roll it forward and back and predict them all. So that's pretty gruesome, and that happened to a real web server. PHP is famous for having a weak random number generator. It's a big thing, and I'm sure this is the key to quite a few of the capture the flag contests we've been in. I didn't succeed, but this is the idea. They use these numbers: an IP address, the time at token creation, the microseconds at token creation, and then they run it through a linear congruential generator. So if you can guess those numbers and get close, you don't have to try too hard to predict them. But what's interesting is even though someone found the vulnerability, a mathematician found it in 2001, it was 10 years before someone wrote the attack tool. That was Samy Kamkar, who I've seen quite a few YouTube videos from. I don't know where he's from, but he has a lot of good hacks. And he wrote a tool that will totally do this. He found that he was able to guess all those numbers, and the actual amount of entropy, which is disorder, left was only 20 bits. Now, 10 bits is only 1,000. 2 to the 10 is 1,000. If you have 20 bits, that's 1,000,000. So if you have 20 bits of entropy, you only have to try 1,000,000 cases to find the one that matches, and that's a few seconds on a modern computer. So he wrote some kind of tool that will hack into PHP random numbers, predict those session IDs. So, I mean, the question is, how do you know if something's random? And this is really, really hard. I mean, he has 9999999, and then they say, is that random or not? And the fact is, you don't know that it's not random because it gave you the same answer 6 times. It's a serious mathematical issue. So here's the algorithm he recommends. This is how you test for randomness. You assume that they are perfectly random because that's the case where you can do the math on it. Then you apply a bunch of statistical tests to see if you can disprove the hypothesis that they're random. That's how you always do it. This is how you generally do this kind of statistics. I've done this a lot. And so then that's the point, there comes a certain point when you can say the probability that it is random has been excluded to 95% certainty or 99% certainty or whatever you like. And Burp will do this automatically. So it has a thing called Burp Sequencer where you're putting in a post, and down here you tell it this is what someone is asking. Now you tell it what token it is you want to worry about. You worry about this. You define this cookie is the token we're going to test to see if it's random. Then you let it get hundreds and hundreds or thousands of samples. He said don't even bother with less than 500, and 50,000 is a lot better. And then it will go through bit by bit and decide if it's random. And it found that these bits are random, but these red ones were not random. So some bits in that token were not random. And some are, which means that it's got a structure in the token, which means they did one of these foolish things like put the time here and the user ID here and the email address here or something. And that gives you a clue. So these you can predict, and those you'll have to brute force by trying all combinations. Anyway.
Is there a way to introduce a delay into that, so to make it less detectable, for example?
Well, you can put, most people are very unwilling to put delays on their server because they want more performance. And I don't think it would do any real good. What you could do, though, is like we were talking about in the quiz, you could block repeated address from the same IP address. One thing they talk about at the end is you should take all suspicious submissions and call them intrusion attacks. Like if they're sending you multiple different tokens for the same username or invalid things, that should just be putting your IDS and blocked. That's what you would do. You would detect these attacks because they're not subtle at all. This guy's sending 5,000 requests for the same username with session tokens that keep going up. So that's a pretty good clue that it's not a genuine user trying to do anything. So like 10 logins within 1 minute from the same IP should probably lead to that IP being banned for half an hour or something. That would be a good thing to do.
Oh, so it's not Burp that generates the request, it's the Burp that just collects.
Yeah, Burp is actually doing all these requests to the server.
Oh, he's actually doing it.
Yeah, getting hundreds of them and then doing statistical tests. That's why they say what would be better is if you can actually download a copy of the software and run it locally. Otherwise, any reasonable server, somebody will probably notice it and block you or something at some point. At least it'll be too slow. All right, so I got a few eye clickers here. So what's the best kind of token? All right, I'll quit at 25. All right, what you would like is a random token. But random is one of these mathematical concepts like a trusted server that is, you can never really achieve it, you have only achieved some approximation of it. And then you just have to argue how random does it have to be? And the answer, of course, it has to be random enough that your attacker can't figure out how to predict it. But that's why you always need threat modeling. And like I say, if it's the NSA, good luck being random enough that they can't predict it. I wouldn't want that job. Right. So what's the easiest to predict? I'll quit at 25. Yeah, maybe I'll quit at 20. Looks like I think I only have 20 students. All right, so obviously sequential is the most obvious. All right. And which one doesn't have any apparent pattern, but there is a pattern? I'll quit at 25. All right, and that's, of course, that linear congruential. Does appear random at first glance, but there is a pattern. All right, so let's take a break till 7:10, and then we'll carry on. Let me stop the recording.